Hey everybody, welcome to today's lesson. Today we're going to be talking a little bit about double replacement reactions. I'm going to try my best to keep this video short and sweet for you, but kind of like single replacement reactions, I have to teach you all about a new reference table that we're going to be using, so I'm going to try my hardest to keep it under. So I want to start today's lesson by just giving two examples of double replacement reactions. And unfortunately, as I perused the internet for the videos of these reactions, I was only able to find one. Sorry, so excuse me, we're going to only look at one video today. I couldn't, and I didn't have the materials to just do it at home otherwise, so I would have tried it if I could. All right, let's go ahead and get started. So the first reaction that I wanted us to take a look at, but I just didn't have the materials that I usually do in class, is the reaction using sodium chloride, okay, as a reactant, as well as using, lithium bromide. And again, sodium chloride, very easy to access. Lithium bromide, I don't have that just lying around. I actually contemplated going outside and grabbing some of the salt from the roads since I could, which is calcium chloride, but I didn't really want to touch it with my bare hands, and I don't have any gloves handy. I don't know. So I couldn't do it. I'm sorry. So that's our first reaction that we're going to take a look at. And then our second reaction we're going to look at today is silver nitrate, AgNO3, with sodium chloride as well, NaCl. Okay, now something that I want to note about double replacement reactions is that the reactants in double replacement reactions must always be aqueous, okay? So I have to take two solutions and I'm going to mix them together in order to see what reaction occurs. So all reactants are aqueous. Okay, so let's go ahead and write out those chemical reactions. So the first one, again, is going to be NaCl plus LiBr. And again, we know this is a double replacement reaction because we're working with a compound plus a compound. And we're really looking at swapping, okay, our Na with our Li because they're both the cations, and then predicting our products. And again, don't forget to re-crisscross as we predict. So Na is a +1, Br is a -1, Li is a +1, Cl is a -1. And so it actually works out nicely that we would just get NaBr and LiCl. Okay, our second reaction today, let's just quickly go through and predict our products. Okay, we have AgNO3 plus NaCl. And from this reaction, again, we want to swap our metals. So Ag and Na are going to swap spots. And we are going to get, again, re-crisscross, but Ag is a +1. Cl is a -1, Na is a +1, and NO3 is a -1. So again, it works out nicely, all 1-to-1 ratios. So we get here AgCl and NaNO3. Now, I'm going to go ahead and I'm going to show you reaction number 2, and then we'll talk a little bit about reaction number 1. So let me go ahead and pull that video up. Yes, perfect. Here we go. And let's go ahead and take a look at this reaction. So here we have our two aqueous solutions, sodium chloride and silver nitrate. And when we add the NaCl to the silver nitrate dropwise, okay, notice that there is going to be this white precipitate that forms. And I love this reaction because it really reminds me of snow. And with all this beautiful snow we got this week, I just thought this was a great reaction to show. Okay, so excellent. Let's go ahead then and jump back to our sheet. Okay, and we will go from there. So, okay, so what we noticed here from this reaction was that there was a white precipitate which we will redefine again, but we have talked about it, that formed. Okay, and unfortunately, or rather, I mean, I guess it's not that unfortunate. It's sad that I couldn't do the reaction that I wanted to with you guys, but it's not that unfortunate because guess what? If I were to complete sodium chloride plus lithium bromide for you, there would be no evidence of chemical reaction. And so our main focus for today is going to be to discuss why are there sometimes double replacement reactions, but not other times? Or why was there no reaction for the first reaction, but there was a reaction for the second? So just really, really quickly, I want to review again evidences of chemical change. So just so that in our notes, we have effervescence, which again is the formation of gas or bubbling. Okay, we have precipitation, which again is the formation of a solid, but again, we'll talk about that in just a little bit. We have heat or light that's produced. We have color change. And another one that we haven't quite talked about, and I don't really love introducing it this early in the year because we haven't talked about acids and bases yet, but pH change is also considered evidence of chemical change. And it will come into play in today's lesson, and we'll talk about that as we get to it. So in order for a double replacement reaction to occur, so just right off the bat, in order for this double replacement reaction to occur, there is something that must be true, okay, of our substance, okay, or of our reaction. So in order for a double replacement reaction to occur, a product must be a precipitate. So one of our two products created must be a precipitate, or I put in parentheses H2O. If H2O is a product, then that will also result in a successful double replacement reaction. So what exactly is a precipitate? A precipitate is an insoluble solid that emerges from a liquid solution or from an aqueous solution. Okay, and so think back, we've talked about solubility, we've talked about this term. If something is insoluble, that means it does not dissolve in water. Okay, so in order for a double replacement reaction to happen, one of our two products must be insoluble in water. Okay, perfect. So how are we going to determine if something is soluble or insoluble? And this is where our newest reference table is going to come into play. Okay, and so we do have a new reference table that we're going to use to help us determine our solubility rules, and that is reference table F. Okay, reference table F, the solubility of ionic compounds. Now, I thought I had pulled this up for us to use, but let me just go ahead and quickly pull it up again so that I can physically write on it. Every year that I teach this lesson, I always urge my students to actually just physically write on the reference table for this, just to help them using reference table F. So if you have your reference table handy, grab it, pause the video, grab it, and let's write directly on this reference table. If you don't have a hard copy of your reference table, I really urge you to print one out. Okay, cool. So here's reference table F. It is literally the solubility guidelines for aqueous solutions. Now, there are two parts to this, right? You can see there is the left side and the right side, and they are similar but slightly different. So let's go through the left side. Okay, the left side says ions that form soluble compounds. Okay, ions that form soluble compounds. That means that these are always soluble. Okay, and then you'll notice that there are some exceptions. Unless paired with, okay? So what does that mean? Well, let's look at the first row here. Group 1 ions like lithium, sodium, rubidium, okay? They are always soluble unless paired with. But guess what? There are 0 exceptions here, Okay, so that means literally any compound that contains a group 1 ion will always be soluble. There are no exceptions to that rule. Okay, let's slide down here a little bit to the bottom where there are some exceptions. Halides like chlorine, bromine, iodine, fluorine, they are always soluble unless they are combined with silver, lead-2, or mercury. Okay, so that means that if your compound contains a halide, that it will always be soluble unless it is silver, lead, or mercury. Okay, now our our right-hand side over here. Okay, our right-hand side over here, this is slightly different because these are ions that are always insoluble. Okay, so actually let me go back, to this here with these exceptions, and just to really drive it home, right, these would be insoluble. Okay, now ions that are always insoluble, okay, again, unless paired with, okay, unless paired with these. So for example, carbonates are always insoluble. If you have something that is a carbonate, it's going to be insoluble unless it is paired with a group 1 ion or ammonium. So then, again, with these exceptions, then these become soluble. But that makes sense, right? We just learned from the left-hand side that group 1 ions are always soluble. So if carbonate is always insoluble, unless it's paired with group 1, it's because group 1 is always soluble. So a lot of rules here, and we'll talk about using them now. Okay, so let's flip back to our notes sheet, and let's practice using that reference table F to determine the solubility of ionic compounds. So when I am looking at using this reference table, okay, what I like to do is I like to take a look first at my first ion, and I say, is there a rule specifically about magnesium? And if you scan through the reference table here, you're going to notice that there is no rule about magnesium, okay? You'll notice that that magnesium does show up in one of the exceptions column, but there is no rule about magnesium. Okay, so then I skip to my second ion. Is there a rule about sulfide ions? Okay, and as you scan through your reference table, you'll notice that there is a rule specifically about sulfide ions. Okay, this rule right here is all about sulfide ions, and sulfide ions are always insoluble unless they are paired with something that is from group 1 or ammonium. So magnesium sulfide is going to end up being insoluble because this magnesium is not group 1 or not ammonium. Okay, let's do a couple more from this and then we'll move forward. Okay, so ammonium chloride. Okay, is there a rule specifically about ammonium? Let's take a look. Scanning through, boom. There is a rule specifically about ammonium. Ammonium is always soluble, and there are no exceptions to this rule. So that means that ammonium chloride is going to be soluble, okay? Again, no exceptions. If ammonium is present, it's always soluble, okay? Let's do last one here for now. Okay, lead-2 sulfate. So I'm going to go back to my reference table and I'm going to say, is there a rule specifically about lead-2? And I'm scanning and I don't see anything, and I'm scanning and I don't see anything. Okay, great. No rule about that. Is there a rule about the sulfate ion? So I go back and I scan and I'm scanning and I'm scanning, and boom, sulfate ion. So sulfates are always soluble unless combined with silver, calcium, strontium, barium, or lead-2+. So compound lead 2 sulfate is insoluble, right? Again, Pb2+ is an exception to that solubility rule. Cool. So if you'd like, feel free to pause the video and try these other substances just to test your knowledge. But at this point, I'm just going to go ahead and give our answers. And so again, pause here now if you want to test yourself. Okay, so lithium hydroxide contains a group 1 ion, so therefore it's always soluble. Okay, aluminum carbonate. Aluminum, there's no rule for, but carbonates are always insoluble, and aluminum is not an exception to that rule. And AgCl silver chloride, no specific rule about silver, but chloride falls under the halides, which are always soluble unless paired with silver, lead, or mercury. So this is actually going to be insoluble again because Ag+ is a exception to that solubility rule. Cool. So before I jump down and do these practice problems really quick, I'm probably going to just do 1 or 2 of them with you. I do want to just scroll really quickly back up to this top reaction and just quickly talk about why we saw no reaction then. So for this first reaction, okay, Na is a group 1 ion and lithium is also a group 1 ion. So remember, in order for a double replacement reaction to occur, that means that that one of our 2 products has to be insoluble. But if both of our 2 products contain group 1 ions, then that means that it's going to be soluble. So there is no insoluble product on this reaction. On reaction number 2, right, sodium is a group 1 ion, so it is in fact soluble, so that's not our precipitate, but we just saw from our table that silver chloride actually produces a solid, and silver chloride is the reason why we have a precipitate or why our double replacement reaction moves forward. All right, let's do just 1 or 2 examples together. So first example here, okay, again, you're going to predict the products to determine if there is a reaction. So yes, you actually do have to predict the products for all these reactions. So Li is going to swap with Na. Okay, we're going to get LiNO3. Again, you should determine all of the charges of these ions to see how they're going to combine. But lithium is a +1, sodium's a +1, chlorine's a -1, nitrate's a -1. So lithium nitrate and sodium chloride. Okay, now we need to look at our rules. So Li is a group 1 ion and sodium is a group 1 ion, and therefore this would result in no reaction. There is no insoluble product. Okay, let's try our next reaction. Okay, sodium, again, that's a +1, hydroxide -1, hydrogen +1 in this case. Again, hydrogen doesn't really form well, I don't want to say that it doesn't form a +1 or -1, but it's going to act as our cation in this case, and Cl is the -1. Okay, that means Na is swapping spots with H, and we end up with HOH, or how do we rewrite that? That's H2O, and we end up with NaCl. Now, in terms of our solubility rules that we've been talking about, HOH, we didn't talk about that yet, but Na is group 1, so this is soluble. But remember up top, I said that there were 2 ways double replacement reactions could occur. Okay, it can occur if there is a precipitate or if H2O is a product. And up here, I talked about how if there's a pH change, then that could result in a chemical reaction. Now, this reaction that we see here, sodium hydroxide and hydrochloric acid, This is actually what we call a neutralization reaction. It's taking an acid and a base and it's producing water. So there's a pH change. This results in a pH of 7. And so yes, there is a double replacement reaction. Okay, I'm going to pause here. If you'd like to, please go ahead and feel free to try that last problem, and we'll start our class with that tomorrow. All right, everybody, thank you so much. You guys have a great day.